In this video, we take a closer look at turning. As explained in the video on the basics of machining, the circular cutting motion during turning is generated by the rotating workpiece, while the tool performs the infeed and feed motions. Since the cutting edge of the turning tool is continuously engaged, turning is also referred to as a continuous cut. Depending on the generated surface and the feed direction, that is, whether turning is performed transverse or longitudinal to the axis of rotation of the workpiece, different turning processes are distinguished. To produce a specific diameter on a turned part, the so-called longitudinal turning is applied. In this process, the infeed at the beginning of the turning operation is made in the radial direction. The depth of cut, AP, corresponds to the reduction of the radius. It should be noted that the infeed value on the lathe always refers to the diameter. For example, if an infeed of 2 mm is set on the lathe display, this refers to the diameter. This means that with an infeed of 2 mm, the diameter is reduced by 2 mm. The depth of cut, AP, which always refers to the reduction of the radius, is 1 mm in this case. During longitudinal turning of relatively long workpieces, which are at least 3 times as long as their diameter, a center tip must be used to avoid vibrations caused by imbalance. For this purpose, the rotating center tip is mounted in the quill of the tailstock, while the workpiece receives the center tip through a center hole. The drive for the rotational movement is provided by electric motors that drive a main spindle, on which the chuck for clamping the workpiece is mounted. The feed, which is linked to the spindle speed, is transmitted to the tool carriage via a so-called feed rod. As the name suggests, in longitudinal turning the feed moves parallel to the axis of rotation of the workpiece, thereby producing a cylindrical surface. Due to the continuous cutting action in longitudinal turning, relatively long chips can be generated, which are also referred to as continuous chips. However, by selecting an appropriate rake angle on the cutting edge, short breaking chips can also be produced. These segmented chips reduce the risk of long chips getting entangled in the rotating workpiece and causing damage. Additionally, this greatly improves workplace safety, as no long chips are thrown around. Depending on the application, turning can be performed with or without coolant. Let us take a closer look at the geometry of a turning tool with an indexable insert. Depending on the feed direction, the cutting edge of the insert has a main cutting edge and a secondary cutting edge. The main cutting edge performs the primary cutting action and is oriented in the feed direction. Accordingly, there is also a main clearance face and a secondary clearance face. The rake face is the same in all cutting cases. In addition to turning tools with carbide indexable inserts, there are also turning tools with brazed carbide tips. In rare cases, turning tools made of high-speed steel are still encountered. However, indexable inserts have the decisive advantage that a wide variety of consistently reproducible cutting geometries can be selected, allowing optimal adaptation to the given requirements. Furthermore, screwed or clamped indexable inserts can be quickly replaced when worn. Compared to cutting edges made of high-speed steel, carbide indexable inserts allow significantly higher cutting speeds. The illustration shows the wedge angle, clearance angle, and rake angle of the cutting edge for longitudinal turning. With a positive rake angle, the rake face slopes downward to the rear from the perspective of the main cutting edge. In contrast, with a negative rake angle, the rake face slopes upward to the rear. This automatically increases the wedge angle, making the cutting edge more stable. For this reason, a negative rake angle is used when machining very hard materials. The rake angle, from the given perspective, describes the inclination of the rake face in the axial direction of the turned part. In addition, the rake face can be inclined not only in the axial direction but also in the radial direction. In the present case, the indexable insert is not inclined in the radial direction. However, it can, for example, be inclined downward in the radial direction as shown. An inclination upward in the radial direction is also possible. Both the radial and axial inclinations ultimately determine the position of the rake face and thus influence chip formation. To define this radial inclination angle, we need to look at the indexable insert in the axial direction. The inclination angle lambda is then the angle measured in the radial direction between the main cutting edge and the horizontal. Like the rake angle, the inclination angle can be either positive or negative. With a positive inclination angle, the main cutting edge, as shown, slopes downward in the radial direction. In contrast, with a negative inclination angle, the main cutting edge rises outward in the radial direction. A negative inclination angle causes the material to be cut not at the tip of the cutting edges, but further outward. This reduces the load on the cutting edge corner and decreases the risk of cutting edge breakage. Especially in heavy machining operations, such as roughing, a negative inclination angle in the range of -3 to -8 degrees is typically used. However, negative inclination angles are disadvantageous in finishing because the chip is directed by the rake face inclination toward the machine surface, which can cause damage. Therefore, a positive inclination angle is recommended for finishing, as it directs the chip away from the workpiece surface. A positive rake angle can also be beneficial when machining materials prone to adhesion. In principle, not every indexable insert can be positioned to allow turning with both positive and negative inclination angles. For positive inclination angles, the flank angle of the cutting edge must necessarily be larger than the inclination angle itself. Otherwise, the flank face would rub against the workpiece surface. Inserts used under these conditions are referred to as positive inserts because they are designed for positive inclination angles. These positive inserts essentially have a sharp profile. In contrast, when a negative inclination angle is used, no flank angle is essentially required, since the negative inclination of the insert automatically creates a clearance angle relative to the workpiece. In these cases, an orthogonal profile for the insert is chosen. This has the advantage that cutting edges can be present on both the upper and lower sides, allowing the insert to be simply reversed when worn. Inserts with such orthogonal profiles are called negative inserts, as they are specifically designed for negative inclination angles. In addition to viewing the indexable insert in the radial direction to define the rake angle, and in the axial direction to define the inclination angle, we now look at the insert from above. Here, another geometric angle can be defined, the so-called nose angle epsilon. This angle is formed by the main cutting edge and the secondary cutting edge. The larger the nose angle, the greater the stability of the cutting edge and the lower the risk of cutting edge breakage. Furthermore, the increased surface area improves heat dissipation and reduces the thermal load on the cutting edge, which in turn positively affects tool life. The corner where the rake face and the flank faces meet is called the cutting edge corner. This cutting edge corner is not sharp but rounded for better stability of the cutting edge. The corresponding radius is referred to as the nose radius or epsilon or cutting edge radius. Large nose radii result in stable cutting edges and allow high feed rates and deep cuts, as required during roughing. Additionally, the large rounding improves heat dissipation, which positively affects tool life. During roughing, nose radii typically range from about 1 to 2 millimeters. However, due to the larger contact area at the rounding with large nose radii, high radial forces arise on the turning tool, which can cause strong vibrations. This then deteriorates surface finish, dimensional accuracy, and form accuracy. In such cases, a smaller nose radius should be selected. Furthermore, a smaller nose radius often leads to better chip breakage, reducing the risk of long continuous chips. Nose radii should be chosen to be smaller than the depth of cut to achieve a high surface quality. Additionally, the feed rate during roughing should be less than half the nose radius. For finishing, the feed rate should not exceed 1/3 of the nose radius. The angle formed during turning between the main cutting edge and the workpiece surface to be produced is called the approach angle kappa. The approach angle influences chip breaking, the forces that occur, and consequently the tendency to vibrate. At the same depth of cut, the smaller the approach angle, the longer the cutting edge engaged in the cut and the better the cutting forces are distributed. This reduces the load on the cutting edge and results in thinner chips that break more easily. Additionally, heat dissipation occurs over a longer edge, leading to lower temperatures and reduced wear. Conversely, with a large approach angle, the chip is relatively thick at the same feed rate and depth of cut, and the cutting edge load increases because only a small part of the cutting edge is engaged, and the cutting forces cannot distribute as well. The short cutting edge length also reduces heat dissipation, which thermally stresses the cutting edge and leads to increased wear. Approach angles of 90 degrees or more are required when producing right-angled shoulders. Angles greater than 90 degrees have the advantage of slightly increasing the effective cutting edge length engaged in the cut. However, this inevitably reduces the nose angle epsilon, which in turn leads to a less stable cutting edge. As already mentioned, the approach angle not only influences chip removal but also affects the forces acting on the turning tool and the workpiece. By decomposing the forces at a given approach angle, it quickly becomes clear that the normal force of the cutting edge can be resolved into an axial component called FF and a radial component called FP. The force in the axial direction corresponds to the force with which the turning tool must be moved during longitudinal turning in the direction of the feed to machine the material. This axial force is therefore called the feed force FF. However, as the force decomposition also shows, a radial force FP inevitably arises, which tries to push the workpiece radially outward. This pushing force is also called the passive force FP because it does not contribute to the machining process but basically corresponds to the force required to hold the turning tool in the radial position so that it is not pushed away itself. When turning long, thin shafts, a large passive force can cause significant bending of the workpiece, leading to poor dimensional and form accuracy. Additionally, the high passive force increases the tendency for vibrations. The passive force can be significantly reduced by choosing larger approach angles. The force decomposition clearly shows that the passive force decreases as the approach angle increases and even becomes zero at an approach angle of 90 degrees, effectively disappearing. Therefore, during finishing, an approach angle as close as possible to 90 degrees should be used, as this generates minimal passive force. To summarize the most important points, small approach angles reduce the load on the cutting edge due to the longer effective engagement length and improve heat dissipation. However, the passive forces, which cause bending of the workpiece and vibrations, are relatively large at small approach angles. Therefore, during finishing or when turning long, thin workpieces, a large approach angle around 90 degrees is chosen. This also clearly shows why the depth of cut should generally be larger than the corner radius. If the depth of cut is smaller than the corner radius, the cutting is no longer performed by the straight cutting edge but by the corner itself. The effective approach angle then decreases as the depth of cut decreases. This results in very large radial passive forces, which on one hand push the workpiece radially outward and on the other hand can lead to increased vibrations. Therefore, even during finishing, a minimum depth of cut must not be undercut, which should generally be larger than the corner radius. A few words about tool wear in longitudinal turning. Paradoxically, the depth of cut has only a minor influence on the tool life. Although the absolute load on the cutting edge increases with increasing depth of cut, the length of the cutting edge engaged in the cut also increases proportionally, so the load per millimeter of cutting edge remains almost constant. Therefore, large depths of cut allow for economical machining of turned parts. Additionally, fewer individual machining steps are required, which positively affects the tool's overall usage time. The feed rate, however, has a much greater impact on the tool life. Especially high feed rates increase heat generation and thus thermally stress the cutting edge strongly. Large feed rates therefore not only reduce the tool life but also worsen the surface quality due to relatively large feed marks on the workpiece surface. Too low feed rates during finishing may cause very long chips, which can also damage the surface. Cutting speed has an even greater effect on tool life. At high cutting speeds, heat generation increases significantly. This causes the cutting edge to overheat, and the strength of the cutting material decreases, meaning the cutting edge essentially softens. This results in increased wear of the cutting edge. However, cutting speeds that are too low should also be avoided, as this can cause material to stick to the rake face. This phenomenon is called built-up edge formation. Such built-up edges lead to poorer surface quality and ultimately to increased wear. Therefore, the manufacturer's recommended cutting speeds should always be observed. In the following, the different turning methods will be examined in more detail. In the case shown so far, a cylindrical surface was produced by longitudinal turning. With the present indexable insert and the chosen approach angle, it is also basically possible to machine the face of the workpiece flat. The feed moves perpendicular to the axis of rotation. This method is also called facing. In this case, the actual cutting work is performed by the previously mentioned secondary cutting edge, which becomes the main cutting edge in this case. It should be noted that not all indexable inserts are suitable for both longitudinal turning and face turning due to their different shapes. We will discuss the various shapes of indexable inserts and their designation system in more detail later. Another turning method is thread turning. In this process, the shaft section where the thread will later be cut is turned to approximately the nominal diameter. A 45-degree chamfer to the thread root facilitates later screwing on of the nut. If the nut is to be screwed up to the shaft shoulder, a so-called thread run-out or thread relief must be made beforehand, allowing the thread to run out into the open. Very sharp indexable inserts are used to machine the thread run out. The thread itself is produced with special threading inserts whose cutting edge has the shape of the desired thread profile. During thread turning, the feed must be precisely matched to the spindle speed so that the thread forms with the correct pitch. The required feed corresponds to the pitch of the thread to be made. To achieve such exact synchronization between spindle speed and feed, lathes are equipped, besides the feed rod often designed as a hexagonal shaft, with a lead screw. This is usually a trapezoidal threaded spindle that converts the spindle's rotary motion into a feed movement very precisely via a lock nut. In contrast to CNC thread turning, on conventional lathes the thread is usually cut at the lowest possible spindle speed to have maximum control over the cutting process. The thread is often produced not in one pass, but in several passes. With each pass, approximately 0.1 mm of cutting depth is added until the full thread depth is reached in the final pass. Additionally, special cutting oils must be used during thread cutting to minimize friction. To create a symmetrical clearance angle on the thread flanks, called the flank clearance angle, and to ensure a correct thread profile, the insert must be tilted according to the thread's lead angle. To achieve this axial tilt of the insert, there are specially inclined spacers for each thread type, called shimming plates, which are placed between the tool holder and the insert. Additionally, these shimming plates are tilted downward by about 10 to 15 degrees in the radial direction to provide a clearance angle in the radial direction. In the case just discussed, a so-called full-profile thread insert was used. This cuts the entire thread profile, including the thread crest with the corresponding rounding. In this case, the initial diameter of the workpiece must be about 0.05 to 0.07 mm larger than the nominal thread diameter before thread cutting. This allowance is then automatically turned down to the nominal size in the final pass by the full-profile thread insert. Since the thread is fully cut, a separate full-profile insert is required for each thread type. For a large number of different threads, this requires a correspondingly large tool inventory. To reduce the number of different inserts, there are also inserts with a so-called partial profile. These cut only the thread root and the thread flanks, but not the thread crests. This way, threads with different pitches can be produced using just one insert. The prerequisite is, of course, that the thread profile cross-section is the same in all cases. The starting diameter of the workpiece must exactly match the outer diameter of the thread without any allowance. Usually, however, a burr forms on the thread crests that must be removed afterwards. For both full-profile and partial-profile thread inserts, many passes are usually required until the final thread depth is reached. Using so-called multi-tooth inserts can significantly reduce the number of passes, as a smaller tooth pre-cuts the thread. This allows for deeper cuts per pass. However, using multi-tooth thread inserts requires very powerful lathes. Next, we will briefly cover additional turning methods. Besides longitudinal turning, facing, and thread turning, grooving turning is another turning process. In grooving turning, the tool cuts radially into the workpiece. This method can be used, for example, to create grooves for retaining or sealing rings. Depending on the required groove width, special grooving inserts are used. Grooves can be made not only on the circumference of a workpiece, but also on its face. For this, the tool cuts axially into the face of the workpiece to produce a circular groove. Parting off is related to grooving turning. In this process, the cross-section of the workpiece is completely cut through in the radial direction. Another turning method is profile turning. In these cases, the cutting edge is shaped as the negative form of the geometry to be produced on the workpiece. Such cutting edges are usually custom-made and therefore relatively expensive. Individual profile turning inserts are mostly economical only in mass production. Turning tools or tool holders for indexable inserts come in different geometries. They are roughly classified into left, right, and neutral turning tools. Mostly, right turning tools are used, which create the desired geometries on the workpiece from the right side. Left turning tools allow machining the workpiece from the left side without having to reclamp the workpiece. Additionally, there are neutral turning tools that enable machining the workpiece from both directions. This is, for example, the case in contour turning, where any shape is produced on the workpiece. Neutral turning tools are also mainly used in grooving and parting operations. The designation depends on which side the main cutting edge is located relative to the tool holder when viewed from the front. If the cutting edge is on the left side of the tool axis, it is called a left turning tool. Conversely, if the cutting edge is on the right side of the tool center, it is called a right turning tool. In all cases considered so far, the workpiece was machined from the outside. However, internal geometries can also be produced on a lathe. Turning tools for external contours are not suitable for this purpose. Due to their rectangular shape, they would collide with the internal surface. Therefore, internal turning is done with special internal turning tools called boring bars. Boring bars are usually made round so that they do not interfere with the internal shape of the workpiece. The standardization of indexable inserts for turning will be explained in the following. The designation of an indexable insert follows ISO standard 1082. This standard divides the designation into a total of 9 blocks, each containing either letter or number codes. Let's take a closer look at the given designation of an indexable insert. The first letter in the designation indicates the shape of the insert. In our case, the letter C stands for a diamond-shaped insert with an 80 degrees corner angle. The second letter indicates the flank angle. Here, the letter N means a flank angle of 0 degrees. The third letter in the designation specifies the tolerance class for the inscribed circle, the gauge dimension, and the insert thickness. In our case, the specific tolerance values can be found in the corresponding column M. The fourth letter in the designation provides information about the characteristics of the rake face and the mounting of the insert. In our case, the insert has the shape G. After the first 4 letters, numbers follow, always in pairs. The first 2 digits indicate the length of the cutting edge in millimeters without decimal places. 4 single-digit numbers, a leading 0 is added. In our case, the cutting edge length is therefore 12 millimeters. The next 2 digits in the insert designation indicate the insert thickness in millimeters, again without decimal places. The exact values can be taken from the illustrated table. Again, a leading 0 is added for single-digit numbers. In our case, the insert thickness without decimal places is 4 millimeters. The following digits in the designation specify the corner radius of the cutting edge. This is given in tenths of a millimeter. Leading zeros are added for single-digit numbers. In our case, the designation 08 means a corner radius of 0.8 millimeters. Letters follow again in the designation. The penultimate letter indicates the shape of the cutting edge. There are sharp, rounded, chamfered, or chamfered and rounded cutting edges. In our case, the letter T stands for a chamfered cutting edge. The last letter in the designation indicates the cutting direction. This cutting direction refers to the previously explained classification of tool holders into left, right, and neutral turning tools. In our case, the letter R means an insert for a right tool holder. The standardized designation of the insert is now complete. Manufacturers can optionally add further information separated by a hyphen. For example, regarding the shape of the so-called Chipbreaker step. What this Chipbreaker step means will be explained next. Chipbreaker steps are steps integrated behind the cutting edge of the tool, located directly on the rake face. The chips produced are deflected by these geometries in such a way that they break at regular intervals. This prevents the formation of long continuous chips and produces short, easily breakable chips. Chipbreaker steps can have very different geometries, so it is important to follow the specific recommendations provided by the manufacturers. In the next video, we will take a closer look at the calculation of spindle speed and the setting of feed rate and cutting depth during roughing and finishing, using a specific example.